Diagonalization is what we're going to be talking about right now. So let's just lay some ground rules for what we're going over in this video and what we'll need to know in general. So this will not include any orthogonal diagonalization questions. The two specifically orthogonal diagonalization questions we've had are in their own separate video, and they really deserve their own separate video. That's a whole kind of different beast and process in a lot of ways. But some of the things from that video will be helpful here. So in here we'll be dealing with both diagonalizing matrices and just determining whether or not matrices are diagonalizable. So let's figure some things out. Okay, one thing that might come in handy is that if we have an n by n matrix with n distinct eigenvalues, our matrix will be diagonalizable. What else? Okay, a symmetric matrix, so one that is equal to its transpose, is also always diagonalizable, and that right there should be good enough for us to figure this one out. So 23, we're looking for the matrix that is not diagonalizable. Let's go straight away and cross off all the ones that are symmetrics, like C and D, and all of the ones with 3 distinct eigenvalues, because these are 3 by 3 matrices. So because this is an upper triangular matrix, our eigenvalues for E are 5, 0, and 7. So that one's good. B, you can mess around with it a little bit, or actually we can just solve for these eigenvalues. This will be 1 minus lambda multiplied by the determinant of this matrix, which is 5 minus lambda times 9 minus lambda. So yeah, we get 1, 5, and 9. Those are three distinct eigenvalues. So B is diagonalizable, and this guy is clearly not diagonalizable. We get eigenvalues of 0 with a multiplicity of 2 and 3, and the only way that this would end up being diagonalizable is if we plugged in 0 to this matrix, to A minus lambda I, and we got 2 free variables. If we ended up with 2 free variables, we would get 2 eigenvectors, and in the end we'd end up having 3 eigenvectors, and we would be able to span R3 with our eigenvectors and diagonalize our matrix. But if we plug in minus lambda, minus lambda, minus lambda, if we plug in 0 for all those lambdas, well, that does nothing to our matrix, and we see that we still have 2 pivot positions. Thus, we don't get our 2 free variables, and A is not diagonalizable. Okay, moving on. 21, let's find a non-singular matrix P such that P inverse multiplied by that guy multiplied by P is equal to that diagonal matrix. So you could move these P's and P inverses over to the other side, and you would have things in a normal kind of form for diagonalization. But really all we are doing is finding the eigenvectors of this matrix here, and we're very nicely given our 3 eigenvalues encoded in this diagonal matrix, which makes our lives a lot easier. So for lambda equals 1, if we plug that in, we will get 1, negative 2, 1, negative 1, 2, negative 1, 2, negative 4, and 2. We can turn this into a 1, negative 2, 1, use row 1 to set both row 2 and row 3 to zeros, and we can solve for our eigenvectors. Because x2 is free and x3 is free, we can rewrite this equation up here equal to 0 as x1 is equal to 2 x2 minus x3. And so if we're making an x2 vector, it will have 2, 1, 0, and an x3 vector will include negative 1, 0, 1. So there we go. Those are our 2 vectors corresponding with lambda equals 1. For lambda equals 6, what will A minus lambda I give us then? We will get negative 4, negative 2, 1, negative 1, negative 3, negative 1, and 2, -4, and -3. Let's row reduce this. Let's subtract 4 row 2's from row 1. So +4 plus 12 is 10, plus 4 is 5, so this becomes 2, 1. Let's add 2 of those to row 3. Gives us a 0 and a -1 there. And what else? Let's add 2 row 2's to row 3. That gives us a 0, a -6, and a -3. So this can become 2, 1. We can set that to 0, 0 using row 1. And let's flip all of these guys. And let's multiply this to 2, 6, 2, and subtract 3 row 1's from it. We get 0, -1. So if we were to make a vector out of our free variable here, which is x3, x3 is going to be equal, we'll get 1, -1, 2, like that. Okay, so we have our three eigenvectors, and we should be able to match these up with our solution. So 1, -1, and 2 should correspond with our third column to line up with 6. We see that here, and our other two vectors, match exactly. So A is our correct answer. 22, which of the following matrices is not diagonalizable? So if a matrix is symmetric, it is definitely diagonalizable. That means that A is diagonalizable, C is diagonalizable, D is diagonalizable, and so is E. Well, wasn't that easy? Let's make sure that B isn't diagonalizable by plugging in our eigenvalue. We see that lambda is equal to 2 with a multiplicity of 2. So when we plug in lambda equals 2, we want to get 2 free variables. But we only get one free variable, and one eigenvector in R2 cannot span R2. Thus, we cannot diagonalize this matrix. 18, let A be a 2 by 2 matrix. Suppose A has those eigenvalues with corresponding eigenvectors. We're finding a to the 16th. So we know that diagonalization can help us out here because a to the k is equal to pd to the k p inverse. So really all we have to do is figure out what our matrices D, P, and P inverse are, and then compute that right-hand side. So the matrix D will be composed of, D is just the eigenvalues on the main diagonal, so I, 0, 0, -I, and then P will be the corresponding eigenvectors for those eigenvalues, which we want to keep them in the correct order, so we get 1, I, and 1, -I. Now the inverse of this is a little tricky, so P inverse is equal to 1 over the determinant of P, which is -2I, and we're multiplying that by, well, let's switch the A and the D position, so -I, 1, and flip the signs on the B and the C position, so -I, -1. Okay, so now multiplying in this 1 over 2I, we get 1 over -2I over -2I. So both of these will become 1/2, and then we have 1 over -2I, so 1 over 2I there, and 1 over -2I. Now if we want to rationalize these guys, we can say that P inverse is equal to 1/2, 1/2, those are good, and then let's multiply the top and the bottom of both of these fractions by the conjugate of that I, so -I. We get -I over 2I times -I. Well, I times -I will just be 1, so we get -I over 2, and then we have -I over -2, over 2 times I times negative I. So we'll get 2 up here and 2 up here and I over here. So we get I over 2. There we go. So let's now just compute everything out. We'll need to compute p times d to the k. Let's actually just write this out. So a to the 16th is equal to p, which is 1i, 1, negative I, multiplied by d to the 16th. I to the 16th is 1, and so is negative I to the 16th. And then we're just multiplying this by p inverse, which is 1/2, 1/2, negative I over 2, I over 2. Now, multiplying by the identity matrix in the middle will do nothing, so we can get rid of that guy and just compute this as our final computation. We get 1, 0, 0, 1/2 plus 1/2 is 1. So we get the identity, which is just A. Which of the following matrices are diagonalizable? Well, the two rules that we can use here is any symmetric matrices are diagonalizable, so that's diagonalizable and that's diagonalizable. And any n by n matrix with n distinct eigenvalues is diagonalizable. So this has eigenvalues of 1, 0, and 6. So 3 distinct eigenvalues, 3 by 3 matrix. That guy is all good. What about number 1? Let's solve a minus lambda I. That's 1 minus lambda times negative 2 minus lambda minus 4 is equal to 0. Lambda squared plus lambda minus 2 minus 4 is minus 6 is equal to 0. Lambda plus 3, lambda minus 2 is equal to 0. So lambda is equal to 2 and negative 3. And as a result, looks like we have two distinct eigenvalues there. So yeah, 1, 2, 3, and 4, they're all diagonalizable. 15, we have a here. We're looking for a to the 6th. Yet again, this is just an easier version of this complex valued matrix exponentiation question. So let's just do this. We need to diagonalize A. Let's find its eigenvectors and eigenvalues. Well, its eigenvalues are just going to be 1 and 2 because this matrix is upper triangular. So lambda is equal to 1, lambda is equal to 2. So our matrix D is 1, 0, 0, 2. Our matrix P, well, we have to find our eigenvectors. So for lambda is equal to 1, A minus lambda I gives us 0, 0, 1, 1, which we can simplify like so. This says x2 is equal to 0. x1 is our free variable, so there is our eigenvector. For lambda is equal to 2, a minus lambda I will give us negative 1, 1, 0, 0. We can flip that around, and that gives us an eigenvector of 1, 1, which means that P, if we are ordering our eigenvectors correctly so that the one corresponding with lambda equals 1 comes first, we get 1, 0, 1, 1. The inverse of this, P inverse, is 1 over the determinant of P, which is 1. Then we switch the A and the D positions and change the sign on the B and the C positions. So we're ready to go. We know that A to the 6th is equal to P multiplied by D to the 6th, 1, 0, 0, 2 to the 4th is 16, 2 to the 5th is 32, so 64 down here. And then we have P inverse, which is 1, 0, 1, negative 1. So let's not think about that right now. Let's just compute this second half. That gives us 1, 0, negative 1, 64. And our final computation will be multiplying, I need more space here. We'll be multiplying this guy by, keep the order, there we go. Multiplying this guy by that final matrix right there, which is 1, 0, 1, 1. This gives us 1, 0, 63, 64, which is answer choice D. 15, we have a matrix A. We're looking for A to the 32nd power. Great. Same old diagonalization. So let's find our eigenvectors and eigenvalues. We are solving negative lambda times negative lambda minus I squared. I squared is negative 1, minus that is plus 1 is equal to 0. Lambda squared plus 1 is equal to 0. Lambda is equal to plus or minus I. For lambda is equal to I, A minus lambda I gives us negative I, I. We can simplify this down to 1, negative 1, 0, 0, and get an eigenvector of 1, 1, 1 out of that. Additionally, for lambda is equal to negative I, we will get I, simplifying down to 1, 1, 0, 0, so we get an eigenvector of negative 1, 1. So as a result, we can write pretty much everything out. We know that A to the 32 is equal to P, which is 1, 1, negative 1, 1. And then we need to order our eigenvectors correctly, so we'll have I, 0, 0, I to the 32nd multiplied by P inverse. Well, what's the determinant of this matrix here? We get 2, so 1/2. Flipping the A and the D positions, flipping the signs on the B and the C positions. There we go. Perfect. So let's just compute this, and we should have our answer. Sorry, gotta make some more space. Okay, doing this right-hand side calculation first. So getting rid of this for now. I really should draw that the other way because we're computing everything. We're computing everything on this side. Okay, this to the 32nd we will get 1 and 1, and multiplying anything by the identity will just give us what we started with. So we can compress things down, and I'll actually factor this 1/2 in. Why not? 1/2, negative 1/2, 1/2, 1/2. This gives us a final 2x2 matrix with entries 1, 0, 0, 1. So yet again, there's the identity, and that's our answer. 12. Suppose that A is equal to PDP inverse, where P is a 3x3 invertible matrix, and D is given there. So we know that since D encodes the eigenvalues of A, the eigenvalues of A are 1, 2, and negative 3. Now we have a matrix B, which is equal to 2I plus 3A plus A squared. So really what we would like to know is what happens to the eigenvalues of A when we add A to factors of A, when we square A, and when we add factors of the identity to A. And this isn't really something that we went over particularly much. So, this is one I had to do a good amount of Googling for. But what I figured out is this. If lambda 1, and I'll write this over here, if lambda 1 is an eigenvalue of A, then all of this follows. Lambda, I'll just call it lambda. I don't want to write ones. Lambda squared is an eigenvalue of A squared. C lambda is an eigenvalue of CA, where C is some constant, and lambda plus C is an eigenvalue of A plus CI. Okay, awesome. And also, if we add any of these together, the same will be true. So lambda plus lambda squared is an eigenvalue of A plus A squared, for example. So let's use this to figure out whether B is diagonalizable, because B will only be diagonalizable if we end up with three distinct values for our eigenvalues after computing this. So we'll be taking these individual eigenvalues that we started with and applying these four rules on them to see what eigenvalue that turns into for B. So we'll have 1, and then adding 2i, 1 plus 2i, we'll add 2. Then 3a will turn that 1 into a 3, and then a squared will turn that into a 1. So we end up getting, oh wait, I can't count, can I? Yeah, no, I can't. We don't add that there. 2 plus 3 plus 1. 2 plus 3 plus 1 is 6. Whoops. Okay, so next one, for 2, we will have 2 still coming from that 2i, plus 2 times 3, which is 6, plus 2 squared, which is 4. That gives us 12. And then for our final eigenvalue, -3, we'll have 2 from that 2i, minus 9, plus 9 is just equal to 2. So we see that our eigenvalues 6, 12, and 2 will correspond exactly to that diagonal C matrix used to diagonalize B. So yes, we do know that B is diagonalizable because we found 3 distinct eigenvalues for B. And finally, this one is just same old, same old. It looks a little scary, but we should be okay. Let's find our eigenvalues. We get 7 minus lambda multiplied by 2 minus lambda plus 6 is equal to 0. Lambda squared minus 9 lambda plus 14 plus 6 is plus 20 is equal to 0. This is lambda minus 4 times lambda minus 5 is equal to 0. Lambda is equal to 4 and 5. For lambda is equal to 4, we will get, for a minus lambda I, 3, negative 6, 1, negative 2. We can simplify that to 1, negative 2, 0, 0, and get an eigenvector of 2, 1. For lambda is equal to 5, a minus lambda I gives us 2, negative 6, 1, negative 3. So we can simplify that down to 1, negative 3, 0, 0, and get 3, 1 out of that. Okay, awesome. That means that we can pretty much go and write our expression for our diagonalization, which will be a to the 2019 is equal to our matrix P, which is our ordered set of eigenvectors 2, 1, 3, 1, multiplied by our matrix D, which will be 4, 0, 0, 5 to the 2019, multiplied by P inverse, where the determinant of P is negative 1, so 1 over negative 1, multiplied by 1, 2, negative 1, negative 3. So factoring in that negative sign, that is what we get there. Let's compute this. Let's factor this in. We get a 2019 power on both of those, and let's compute these last two to see what we get. We will have a 2 by 2 matrix with entries minus 4 to the 2019, 5 to the 2019, 3 times 4 to the 2019, and minus 2 times 5 to the 2019. Now our final computation will be 2, 1, 3, 1 multiplied by, I'm not copying this over, we'll duplicate it, multiplied by this guy right here. This gives us an even bigger one. We get negative 2 times 4 to the 2019 plus 3 times 5 to the 2019, and we should already be able to pick our answer. Yeah, pick our answer out. That should be A. Let's go compute the rest for fun, though. Even though it's really not fun, we get, oh, great, there's weed whacking going on right outside. Well, Good thing this is almost over. I'm sorry you have to hear that for a second, but don't worry, they will be yelled at. It's my brother, so it's legal. Minus 4 to the 20, 19 plus 5 to the 20, 19, and then over here we get 6 times 4 to the 20, 19, minus 6 times, I do have that, right? Minus 6 times 5 to the 20, 19, and then finally on the bottom we get 3 times 4 to the 20, 19 minus 2 times 5 to the 20, 19. And we are done. And I'm sorry, you probably can't even hear it. It's just bugging me. Okay, see ya.